North America sales manager. I spent the last 12 years driving multinational businesses expansion and strategy for global wastewater treatment companies. Been working specifically on the MABR technology for the last 9 years, together with Fluence, and before that with MFC. You have my contact information, so please feel free to reach out at any point. I would like to start with a short introduction about who Fluence is, since it's a relatively newer brand. Fluence is a result of a merger between two companies. One is RWL Water, which is a holding company to 5 other companies. 2 are based in the United States. One is Aeromix out of Minneapolis, Minnesota. They specialize in surface aerators for lagoon-based applications. The other one is Tipton Package Plants, based out of Batavia, Ohio. They do extended air package plants. Another 2 companies are based out of Israel. One is called Neurosoft, which does decentralized wastewater treatment. Decentralized desalination systems for seawater, desalination, brackish water, and fresh water. Another company is based out of Italy, which does anaerobic digestion for food and beverage mainly. And an Argentinian company that does skin-mounted water filtration systems. So these are the 5 companies building RWL, and in July of 2017, RWL merged with the Israeli company called MFC, which had the proprietary technology of the MABR. We are 350 highly trained water and wastewater professionals spread worldwide. We have experience in over 70 countries with offices in the US, China, Argentina, which in addition, which I will show in a minute. And we are a publicly traded company traded in the Australian Stock Exchange under the ticker FLNC. Our global presence, as you can see, anywhere from China, Australia, Europe, Israel, Africa, or the Middle East, I should say, and of course, the Americas, South America, Central America, and we are headquartered in White Plains, New York, so essentially an American-based company. We're involved anywhere in the water spectrum, so anywhere between ultra pure water and all the way to ultra black water treatment. So if it has anything to do with water, we've probably dealt with it and had experience with it. And with over 7,000 installations in over 70 countries, we feel quite confident to be able to cater any type of client from large to small, where Fluence mainly focuses on the smaller to medium size applications when it comes to the MABR technologies. So a little bit about the MABR. By the way, I forgot to mention, anyone, we encourage you to use the Q&A button at the top of your screens to ask any questions. And later in the webinar, we'll address those questions, of course. So please feel free to write any question and we'll try to answer all of them as time permits. As I mentioned, a little bit about the MABR technology. So MABR is an acronym for Membrane Aerated Biofilm Reactor. You know, in the water spectrum, we are very innovative when it comes to technologies, but not so much to names. So you have MABR, MBBR, MBR, all sounds very similar, but essentially are very different. MABR is an acronym for Membrane Aerated Biofilm Reactor. And typically, as soon as I say the word membrane, the first thing that comes to people's minds is US membranes or MBRs. I need to ask you to forget anything that you know about MBRs or US membranes, because the MABR is a membrane, but acts completely different. And that's why I like typically to start with this slide, which is a process flow diagram of a conventional domestic wastewater treatment. So you will always have your biological part of the process, your pre-treatment part of the process, where solids are being screened out of the process. Then you will have some sort of a biological process to get rid of all the soluble pollutants. And then depending where you are in the world, you may have some further filtration by cloth media filters or UF membranes or any other type of technology, and disinfection. And you'll always have your byproduct, which is sludge. With MABR, the process remains exactly the same, but we're going to focus on the biological part of the process. And I need to ask you to take into consideration that all of the auxiliary equipment around the biological part remains exactly the same and is being designed just like in any other process. So from now on, I'm going to mainly focus on the biological part of the process when talking about the MABR. And by the way, that is why it's so different from MBR, which comes in the back end of the process when it comes to the UF membranes, of course, and so on. So a little bit about aeration. Aeration is probably one of the highest energy consumers in the biological process. And this is it's a timeline representing the development of technologies in the aeration, in a way to introduce air or oxygen to the wastewater. So back in the 50s and all the way up to the 70s, they used to have those surface aerators, which would bring up, which would be installed on the surface of a biological basin, would spin, and any water droplet that would come out to the atmospheric air would get whatever oxygen it could, and then land back into the basin. A highly inefficient way to introduce oxygen to the wastewater, consuming approximately around 3 kilowatt-hour for every kilogram of COD that is being removed. And then in the 1980s, they said, well, if we can introduce the air from the top, why not introduce it from the bottom of the basin, create a nice jacuzzi for the bugs, and make the process a whole lot more efficient. And they did come up with the coarse bubble diffusers. This made the process more efficient when it came to energy, consuming approximately 2 kilowatt-hour for every kilogram of COD that is being removed. And then they said, well, if we can do coarse bubble diffusers, why not do fine bubble diffusers? Make the air bubble more available for the bacteria by increasing the surface area. And they came up with the fine bubble diffusers, which did make the energy consumption more efficient, reducing it to 1.5 kilowatt-hour for every kilogram of COD that is being removed from the wastewater. And please note that comment at the bottom that this includes nitrification, which also consumes oxygen beyond the BOD/COD removal. And that is the technology that is mainly being used today. And then in 2015, Fluence came along, introducing the MABR technology, which is by far the most energy efficient mechanism to introduce oxygen to the wastewater, slashing the energy by over 90% to 0.2 kilowatt-hour for every kilogram of COD that is being removed. So obviously, made a huge technological leap in the aeration, and I will explain about that in a little bit. By the way, this timeline is relevant mainly to Israel, so perhaps in your territory it's a little different, but I believe you understand the picture. So how were we able to make this energy efficient, introducing oxygen to the wastewater so efficient when it came to energy? So basically we came up with this semi-permeable membrane sheet that allows oxygen to diffuse through it, but did not let water flow into it. A matter of surface tension and a coating that we put on top of the membrane to make the energy efficiency a little bit more efficient and more robust. So that's the white material that you see at the bottom right-hand side of the screen. So we've used that material and we created a sleeve out of it by having an approximately 850 feet long sleeve by 3 feet, putting a geotechnical spacer net in between two membrane sheets and welding the circumference. So now we have like a sandwich, a membrane, a spacer, and then another membrane, and the circumference is welded. We have one inlet valve at the beginning of the sleeve and an exhaust valve at the opposite side of it. We would pump atmospheric air into one end of the sleeve at extremely low pressure, less than 0.047 psi. Let the air travel the entire 850 feet long sleeve until it goes out back from the exhaust valve. This is not how we introduce air or oxygen into the wastewater. This is just to maintain fresh air inside the sleeve 100% of the time. For that, we're utilizing the smallest blower available that operates 100% of the time and continuously pushing air from one side of the sleeve to the opposite side. Now we take this sleeve and we roll it up in order to come to this spirally wound shape that you see on the top right-hand side of the screen. The reason that this is black and the sleeve is white is because before we roll it up, we put an additional spacer sheet in order to create spaces from one layer of the sleeve to the next one. Now we take this spiral and we start stacking them up together, just like you can see on the bottom left side of the screen. How many spirals we would stack together, that's a function of how deep the basin that these spirals would go into. So, for example, if you have a 9 feet deep basin, we would probably put 2 of these spirals one on top of the other. If you have a 12 feet deep basin, we'll probably have 3 of these spirals stacked together. If you have a 15-foot basin, 4 spirals, and so on and so on. This is horizontal because this is how it comes out from the factory, but in reality, this will be inserted vertically into the biological basin, into the very beginning of it, and I will explain why. I saw there was a question about the screening required, and I will address that in a short while. I'll see if it's been answered probably. So now, basically what you understand is that we have this, from now on, when I refer to a spiral, I'm going to a spiral tower, excuse me, an MABR tower. It means a few of these spirals stacked together. Okay, and then one moment. Here we go. Sorry about that. So now we're pushing air into one end of the sleeve, and so all of these spirals are basically full of air. And when we put them in a biological basin, we basically need to anchor them down to the basin because it's like putting balloons underneath the water, right? So we anchor them down into the biological basin. And what happens is that when we push the air into the sleeve, the air that we push in there is atmospheric air that has approximately 20% oxygen concentration inside of it. It is submerged in a tank full of wastewater, where in the wastewater you have bacteria naturally developing and utilizes whatever oxygen is available in the biological reactor. Reducing the dissolved oxygen content in the basin almost to 0. That concentration difference between 20% oxygen concentration in the air that we push into the sleeve and almost 0% dissolved oxygen in the biological basin, in the wastewater, is the driving force for oxygen to diffuse from the high concentration side inside the sleeve through our semi-permeable membrane that will allow oxygen to diffuse through it to the low concentration side, which is the wastewater. The nice thing about diffusion is that it's a naturally occurring process that consumes no energy. And that is how we are able to reduce the energy associated with aeration by over 90%. I hope that part is clear. I'm happy to take questions, but again, it's a pretty straightforward and it acts very similar to the human lung, where we all take a deep breath in, it goes into our lung wall acts as a semi-permeable membrane. Air that we breathe into our lung has approximately 28% oxygen, just like the air anybody who's listening to this webinar is breathing right now. Opposite to the lung wall, you have your bloodstream that has almost 0% oxygen because all of the oxygen has been utilized by our vital organs. And again, you have a concentration difference. Oxygen diffused from inside our lung through our lung wall, the semi-permeable membrane, to the bloodstream. We basically biomimic the human lung. And as I explained, diffusion is a naturally occurring process that consumes no energy. So now, when I present this in places where energy is very expensive, obviously this is one of the biggest drivers to adapt the MABR technology. But in the US, energy is not very expensive. It's a nice to have feature, and of course for very big municipal plants, it's a big issue and energy reduction is important. But for smaller plants or decentralized plants, energy is cheap. In the US, it would cost typically anywhere between 6 cents to 10 cents per kilowatt hour. So obviously it's a good driver, but it's not, it's not a huge driver in small plants across the United States. But beyond being a very efficient diffuser, the MABR membrane acts as a wonderful platform for biofilm to develop on top of the membrane. Basically what happens, and I hope this slide is clear, if we were to take one of our spirals and would zoom in, okay, we would go into the sleeve. The dashed line represents our semi-permeable membrane. We all need to imagine there's another semi-permeable membrane on the opposite side where I'm showing my mouse cursor. Air is being pushed towards your screen, into your screen. And as I explained, only oxygen is being diffused into the wastewater because of the concentration difference. So I hope this makes this slide a little clearer. Now, on top of the membrane, we'll have biofilm developing. Now, again, that's why I kept asking you to forget everything you know about UF membranes, because unlike UF membranes, in the MABR process, we promote the growth of biofilm on the membrane. So essentially what will happen, the type of biofilm that will grow on the membrane is the biofilm that love oxygen the most, because adjacent to the membrane wall, that is our oxygen-rich zone, because that's where oxygen is diffuses into. Now, what I've not explained yet is that we installed the MABR towers at the very beginning of the biological basin. At that point, the wastewater has plenty of ammonia, and I'm considering that we're treating domestic type of wastewater. So it'll have plenty of ammonia because that has not been addressed yet. And as soon as the raw wastewater meets an MABR tower and adjacent to the membrane wall, that's the type of biofilm that thrives under those conditions would be the nitrifying biofilm that takes the ammonia in the wastewater and utilizes the oxygen that is being diffused into the wastewater and convert it to nitrate in a process called nitrification. Now, what is interesting about the nitrifying biofilm is that unlike other biofilmic processes, such as RBCs, such as trickling filters, MBBRs, if you would, the type of biofilm that grows on the MABR membrane is a nitrifying biofilm that does not have the capacity or the capability to exceed more than 100 microns in thickness. So this is a very different biofilm from what you're familiar from RBCs and so on, which can get as thick as inches. In this case, the biofilm that grows on the MABR membrane is a nitrifying biofilm that always maintains very, very thin. Okay, as I explained, approximately 100 microns and not more than that. Now, this biofilm is so efficient in utilizing all of the oxygen that we introduce into the system that it creates an anoxic zone behind it. So if you were to take a DO probe and put it in an MABR-based biological basin, you will get anoxic readings because the steady state of an MABR-based basin is anoxic. The only aerobic area is the biofilm. So under those anoxic conditions, which is the majority of the basin, and having no oxygen, having plenty of nitrate as a result of the nitrification from the biofilm, and has enough BOD to support enough BOD because we have not addressed BOD yet. That creates the perfect conditions for denitrifying bacteria to develop, take the nitrate and convert it to nitrogen gas in a process called denitrification. So essentially, we're presenting to you a technology that is able to simultaneously nitrify and denitrify without the need to have two separate basins, an anoxic one and an aerobic one, and without the need to have an internal nitrate circulation. I will repeat that slide shortly because that is probably the most technical part of the presentation. So real quick, as you can see now, we've switched it around. So we're zooming in now. On the left side is air is pushed into your screen on the left side. When you all need to imagine there's another semi-permeable membrane sheet on the left side of the screen. Air is being pushed into the screen. Only oxygen is being diffused through the semi-permeable membrane into the wastewater. Biofilm is developing on top of the membrane. Ammonia is being utilized, is being taken with oxygen. Nitrification takes place. Nitrate is being produced, being discharged into the biological basin. With BOD available at the basin, denitrification takes place, and the nitrate is converted to nitrogen gas. So again, simultaneous nitrification, denitrification. Now, all of this takes place naturally. In other words, the operator, no matter how enthusiastic they are and how they really want to do something, there's not much they can do. This all is being designed by Fluence, in other words, or by an engineer, where when we get the influent parameters characteristics, such as, you know, the concentration of TKN, ammonia, and so on, and we understand what is the effluent requirement, we would design the system in such a way that we would put enough MABR towers in a series, which I will show in a second, to get rid of all of the nutrients. And then you're probably left with some BOD to polish off, and we can and I will discuss how that is being done. But what I'd like you to take from until this part of the presentation is the MABR being an extremely efficient diffuser to introduce oxygen into the wastewater, and B, being a champion when it comes to nutrient removal, mainly nitrogen, and then I will now address about phosphorus a little bit. Now, this is an example of an MABR-based biological reactor. This is obviously one of our products, where we'll discuss this later. The wastewater flow comes from left to right. So as I explained, the first thing the raw wastewater will meet will be an MABR tower. Now, we typically install a selector tank ahead of the MABR biological basin in order to allow for some under anaerobic conditions for the phosphorus to be released by the bacteria and for the BOD being taken in by the bacteria, which I will demonstrate in the next few slides. So the wastewater that flow into the MABR-based basin are coming from a selector tank with about 15 minutes retention time. So it'll go through 3-stage MABR towers in this example to get rid of all of the nitrogen, and it will follow, as you can see, these empty tanks. These will be accommodated by your typical fine bubble diffusers for some BOD polishing, because as I explained, we have not addressed BOD yet. The first pollutant that is being eliminated in the wastewater is nitrogen, and only then is BOD is being removed. Now, for the denitrification process, we do need a carbon source. So unlike conventional processes where first BOD is being removed and only then nitrogen is being removed, and many times they don't have sufficient carbon source to support the denitrification, in this case, that never happens because we're not addressing the BOD. So whatever BOD that is available in the wastewater is being utilized as a carbon source for the denitrification. And only whatever is left after that needs to be polished off, and we do that with fine bubble diffusers. This is from techno-economical reasons, because it's cheaper to put a fine bubble diffuser to remove BOD as opposed for an MABR module. So that is how we ended up designing an MABR-based process where nutrients are being removed by the MABR modules, and then whenever you have whatever BOD you need to polish off, you would do that with fine bubble diffusers. So some results that better explain how we are able to remove nutrients from the wastewater. So again, I'm using the same example that I just showed. Wastewater comes from left to right. In the raw wastewater, you have approximately 50-55 TKN coming in, or ammonia. And you can see that the farther along you go in the process, both ammonia, which is represented by the dark green color, and nitrate, which is represented by the light green or blue color, are being removed together. And that is an evidence to the simultaneous nitrification and denitrification. In conventional processes, what you would see a reduction in ammonia first, a spike in nitrate, and followed by a reduction in the nitrate. As you can see in the MABR process, both pollutants, both ammonia and nitrate, are being removed together. And that is the evidence for the simultaneous nitrification and denitrification. Another thing that we've seen is, well, as I explained, typically you'd have a selector tank to allow biosorption to take place. So you'll have a high COD content coming in the raw wastewater, and then under the anaerobic conditions in the selector tank, as I explained before, the bugs will take in whatever COD or BOD they could and release the phosphorus. So here you can see this is before the selector tank. Stage 1 is after the selector tank. And then you can see the slow reduction in COD. By the way, the reduction in COD in stage 2, 3, and 4 is associated with the denitrification, with the carbon source that is being utilized for denitrification. And that's what happened to the phosphorus, which is the opposite from the BOD or COD. So you come in at about 7, and just like the bugs take in all the BOD, they release whatever phosphorus content they have in their bodies. So you have a total phosphorus spike up at the beginning of the process. But the interesting thing to see here is that basically the conditions around the MABR towers are sufficient to allow for biophosphorus removal process to take place. At the bottom side, you can see our ORP levels at around the MABR modules. So you can see that they could get very, very negative on the verge of anaerobic, which essentially allow for the AOPs to thrive in those conditions. So you're basically getting both nitrogen and phosphorus removal biologically. What we see is between 80 to 90% biophosphorus removal from the process alone. So say you come in at 10 total phosphorus, you can expect to come out between 1 and 2 milligrams per liter. And if you need to polish that further, you can add some chemicals. But the point is that the process supports biological phosphorus removal as well. And as a general note, the entire process is being controlled by the ORP levels. So once they change, we have the controls knows how to recognize that and switch on and off the diffusers, which I will talk about in a second. So some MABR configurations. So until now, I've presented everyone in technology, but what Fluence had done is to take this technology and convert it into products. So in the center, you can see the MABR tower, which is the technology. And then what we had done, we've created a few different products around it. So the main products I will talk to you about today is our spiral package plant or spiral product line, which is basically we've taken the MABR tower and we've inserted it into tanks that we manufacture and create a whole package plant that is from A to Z. So anywhere from the raw wastewater coming in, it needs to be fine screened. I saw there was a question about what is the screening that is required. we are going through the same evolution as MBRs did in the 90s or the early 2000s, where we started with 1 millimeter perforated fine screen ahead of the MABR basin. Today, we're allowing 1.5 millimeter perforated screening ahead of it. And I believe that gradually over time, we'll get more lenient about that requirement, but currently we're talking to 1.5 millimeter perforated screening ahead of it. So it will go, the spiral box consumes the whole package plant, meaning the fine screening. It'll go into the biological reactor. It'll go through a secondary clarification step or a UF membrane, which I will discuss in a little bit. And then it will go through either a media filter and disinfection and so on. So this is your complete package plant. We have those standalone MABR towers, which can be integrated by other package plant vendors out there. So for example, Orenco had previously bought our MABR towers to integrate it into their systems in order to expand the treatment capacities they can handle with their fiberglass tanks. And then we have our Subre product line, which Leon from Black Veatch will talk about in greater detail shortly. But essentially, we're talking about standalone MABR towers that can either be retrofitted into existing municipal wastewater treatment plants in order to enhance nutrient removal, to increase capacity, and to reduce energy, or as greenfield municipal plants that are built around the MABR towers. So a little bit about the spiral product family. What we've done, we've basically created different Lego pieces, if you would, that when put together, you get the complete package plant. So we have different models. If it's the spiral S1, S stands for small, 1 stands for how many MABR towers are in the reactor, a spiral M2, medium, and 2 MABR modules in the reactor, and then the spiral L for large, with anywhere between 1 to 5 MABR towers installed in the reactor. Again, how many MABR towers are installed? That's a function of the nutrient concentrations coming in and the nutrient effluent requirement coming out. Okay, now you can once you put these together, these Lego pieces together, these are complete plug and play solutions. By the way, these looks like cargo containers, but it's very important to mention these are not cargo containers. What Fluence is doing, we are manufacturing water tanks in the same dimensions as cargo containers, and then we certify these water tanks as cargo containers, and that reduces our shipping cost significantly. So that's why they look like cargo containers, but these are water tanks that are being manufactured from scratch. And this is an extremely important feature to explain. In this example, what you can see is a spiral L box coupled with a secondary clarifier. So that teaches you that the MLSS concentration in the biological reactor will be around 4,000 milligrams per liter of MLSS plus minus 250. But this is an interesting example for where we couple our spiral L box with a UF membrane. So MBR plus MABR, and obviously we'll be operating at around 10,000 milligrams per liter of MLSS at that point. So what you can understand from this is that it does not, the MABR towers don't really care the concentration of mixed liquor around them. Can go anywhere from 4,000 to 10,000. It's all a function of the drivers of the opportunity or the application. If footprint is an issue, we will probably go with MBR if at the back end of the MABR. If extreme effluent requirements are there are extreme effluent requirements, we'll go with MBR. But if simple operation is required, we'll probably go with a spiral box followed by a secondary clarifier followed by a sand filter, if you would, and disinfection. And obviously Fluence provides all the configuration or all the solution. So we can play with what configuration it goes. But I like to use this slide to explain that the MABR does not compete with MBR, it complements MBR. It's a feature, it's a component that goes into the biological process in order to enhance the capacity of the biological process. Obviously, we can expand these over time. We can phase it in. So what you see here is a spiral site, if you would, where you would have a multiple number of spiral Ls, followed by a UF membrane and auxiliary tankage that is required. This is an extremely important feature, especially for smaller applications, because in the smaller application, you want to try to invest as little as possible at the beginning, and then invest more only if more sewage flow comes into the plant. That allows you to spread your expenses over time, or your client's expenses over time. So it's a complete modular solution that can be expanded over time, which is an extremely important feature. And again, one of the things that Spiral does is minimizing the amount of civil works that are required. In the United States, civil works are probably the most expensive part of any project. So in these cases, what we see in a Spiral, we are able to get out of the whole project cost, the equipment would cost about 50%, and the civil work supporting that would cost an additional 50%. That's what we're seeing, as opposed to conventional municipal project where the equipment is typically, I want to say, between 15 and 20%, and then the rest is associated with engineering and civil works. So by having a plug-and-play solution, we're able to reduce the amount of civil works are required, and by that, to reduce the cost of a project as a turnkey. Again, this is just another layout of the Spiral site. I don't want to get into this. This is example for a subrate tower. So as you can see, it's all it's a function of how deep the basin that we want to retrofit our modules in. So it can be 1-stack tower, 2-stack tower, 3-stack tower, 4-stack tower, and so on. It is important to explain that at this stage, these are not drop-in, meaning that in order to retrofit an existing municipal plant, we would need to drain the basin, install the MABR reactors or towers, and fill the basin again. So we are working on a drop-in configuration, but at this stage, that's what is required. This is an example of a retrofit, but Leon will talk more about that, so I'm not going to take the time to discuss this. But essentially, we can retrofit into existing facilities. As I explained, the main drivers to do that is to get better effluent quality from the existing facilities, especially when it comes to nutrients, get higher or be able to increase the flow within the same given or capacity within a given infrastructure, and reduce the energy of the plant. Again, these are some examples. This is a project that is taking place in Jamaica for Subaru Greenfield, where they're putting 3 lines with the Subaru Greenfield in Jamaica. That's the technology that was chosen. And now for the remaining, I want to say 5 minutes that I have, I would like to take your time and go over a couple of case studies that are very interesting before I hand it over to Leon. I apologize, I've taken a little longer than I promised, Leon, so I apologize. The first case study is a pilot that we put in Stanford University in California. The facility is called the Kodaiga Resource Recovery Center, which is basically Stanford University that came up with this initiative to test and validate new wastewater treatment technologies. We were their first client. The system was put in Stanford in the beginning of 2018. Again, it's just a pilot, so it treated only 3,000 gallons per day of extremely highly concentrated wastewater. Please note the raw wastewater characteristics: over 1,200 milligrams per liter of COD coming in, over 100 milligrams per liter of TN coming in. We had 2 phases for the pilot, or 2 goals, I should say. One was to meet California Title 22, which mainly talks about tertiary treatment and disinfection. So turbidity of less than 2 NTU and E. coli count of less than 2.2 mpm per 100 milliliters. And then we had a phase 2 there, or second goal, to meet Maryland's ENR requirements, enhanced nutrient removal requirements, which essentially mean less than 3 milligrams per liter of total nitrogen and less than 0.3 milligrams per liter of total phosphorus. So this is the facility, the Kodaikan Recovery Center. As you can see, the slide theme had changed because these are slides that's been generated by Stanford University. So this is the setup. You would have the raw sewage coming from the main sewer line in the vicinity of the site. It would go through a grit removal, and then you could choose what type of wastewater you would want. In our case, we chose the raw wastewater straight after they came from the municipal line. So it would go into the Fluence pilot plant. And this would be the setup within the pilot plant. We would have our own fine screen, 1 millimeter perforated fine screen. It'll go through 2-stage MABR reactors. Again, this is not the spiral configuration. This is a custom designed pilot for Stanford, so they would be able to walk in the container and test the wastewater at all the different stages of the process. So in this case, it went through 2 MABR stages, followed by a secondary clarifier, followed by a sand filter that was put on the roof, a chlorine contact tank for chlorination, and discharge effluent. The goals, as I explained, was to meet California's Title 22 reuse standards, so MTU and disinfection. Here you can see the raw wastewater that we received. As I explained, extremely concentrated sewage. This is just as a reference from Metcalfe and Eddy. These are the medium strength wastewater in the United States. So you can see these were, 3 times more concentrated than conventional sewage in the United States. So we also added the TN requirements for the Title 22 because, again, Title 22 only talked about disinfection and tertiary filtration. So we added the requirement of meeting less than 10 total nitrogen. So here you can see that our average at the effluent was always less than 10. So obviously we were successful in meeting that requirement of being less than 10 total nitrogen. Turbidity was always kept below 2 NTU. So we were successful in this. And in a second, I will show you also the residual chlorine, which represent the disinfection capability we had, but wanted to give some acknowledgement to the people at Stanford that supported our efforts. So Professor Craig Cradle, who basically manages the Kodaikan Recovery Center, and Dr. Sebastian Tillmans, who manages the facility. So these are, again, the turbidity and the total residual chlorine, which basically means that we met the 2.2 mpn per 100 milliliters of total coliforms. And then we went on to the second stage, which needed to demonstrate that we're able to show always less than 0.3 milligrams per liter of total phosphorus in order to comply with Maryland's enhanced nutrient removal requirements, and also total nitrogen of less than 3. And please note the concentration difference. This is bringing it from 111.5 milligrams per liter total nitrogen down to below 3. So obviously successful in this, and we were very happy. That's part of the reason why MDE gave their blessing to our process to be implemented in the state of Maryland. Another last case study, and from there I'll hand it over to Leon. It's a resort, RV resort in the state of Oregon, in La Pine, Oregon. This project has been done with collaboration with Orenco, who is probably one of the biggest fiberglass manufacturer in the United States, and they also have a division that does their own packaged wastewater treatment plants. In this application, we needed to treat the wastewater of a RV resort in Oregon with an approximate 18,000 gallons per day average daily flow with a peak of 42,000 gallons per day. We ended up putting 4 MABR towers of 2 stacked spirals in each tower, integrated into Orenco's fiberglass tanks, it required only 1 tank. Effluent requirements were less than 10 BOD, less than 10 TSS, less than 10 total nitrogen, and you can see the disinfection requirement. So before Orenco chose us as the biological treatment technology, they evaluated 5 different other technologies. So anywhere, obviously, the MABR and BBR, simultaneous nitrification and denitrification activated sludge process, 2 different type of MBR processes, traditional activated sludge process, and Orenco's own textile package bed filter. So they evaluated all of these different technologies, and they've done a complete life cycle cost analysis, both on the capital cost and the operation cost summary. So basically to try and put these together, and what you can see here, that essentially the MABR, which is the 3rd column, came out cheaper both on the capital side and obviously on the operational side. So, and when you combine these 2 together, you see that the MABR was the superior technology. So this was ahead of the selection because of this analysis that the engineer had done. They ended up going with the MABR modules, and the system is now been running for, I believe, about 6 months in Oregon. Showing great results. We're still waiting to collect some more data before we present the results, but we're obviously complying as well. I did forget to mention that for Stanford, the full report is published and available for everyone at the Stanford website. But if anybody would like a copy of the report done by Stanford, please don't hesitate to reach out to us and we'll send it through. So this is my part of the presentation. Here again, you can have my contact information on our website. And at this point, I'd like to pass the stage to Dr. Leon Downing out of Black Veatch, who is a principal process engineer and innovation leader with Black Veatch from Madison, Wisconsin. Leon provides technology leadership in support of Black Veatch process engineering and applied research projects globally. A graduate of the University of Wisconsin, Platteville, Leon obtained his Master of Science and PhD at the University of Notre Dame. Dr. Downing is an active member of several professional organizations. He currently serves as the Vice Chair of the Modeling Expert Group of the Americas, has authored chapters in 4 web books, and contributed to 14 peer-reviewed scientific journal publications. So thank you, everybody. Leon, thank you so much for joining us and speaking in this webinar. I will stop sharing and mute myself and allow you to take over. So 1 second. Here you go. The stage is all yours, Leon.
Thank you, Ronen. Thanks everyone for attending this webinar today. Let me get this presentation up and running. Nope. Let's see. There we go. Ronen, is that showing up?
Yes, it is. Perfect. Thank you.
Great. So I will. I'll try to keep us on track. I know we have about 10 minutes left, so I'll be sort of going over a few items pretty quickly. But first, Ronen spent a lot of time on this. Why focus on the MABR? As an engineering consultant, what's interesting about it to me? So these 2 parts are essentially what Ronen talked about before. But what's interesting is just how we apply the MABR. And when we look at the 2 different ways that we can apply an MABR, there's a biofilm-focused MABR where we're trying to grow nitrifiers and heterotrophs in the same biofilm. We add that oxygen at the base of the biofilm. We get our nitrification at the base with our nitrifiers, and denitrification in our exterior of the biofilm with our heterotrophs. And then if we look at the hybrid MABR, the challenge of a pure MABR, like a pure biofilm application, is that if you have a lot of BOD in the bulk liquid, or even if your organisms are processing that BOD, maybe you can't measure the soluble BOD, but there's a lot of activity associated with BOD oxidation, you can get a very thick biofilm. So some of the first applications of this ended up with several millimeters of biofilm on the membrane surface, and as that biofilm gets thicker and thicker, it's more and more difficult to get the ammonium to penetrate into the depths of the biofilm. So biofilm management, it's always important in kind of a fixed film system. It becomes really critical in an MABR because if you get too thick of a biofilm, this oxygen will still be consumed at the base, and you'll end up not really getting a high nitrification rate. So there's always been this balance of loading conditions and what the bulk liquid conditions look like in the nitrification rate you get, right? And the higher the nitrification rate, which we're saying is the ammonium removed per surface area, the higher that value, the less membrane surface area you need. And that makes the project more economically viable. The hybrid MABR is really where a lot of the application has gone. And this gets into some of the slides that Ronen presented where if we have heterotrophs in our bulk liquid, and so this is almost like a IFAS type configuration, integrated fixed film activated sludge, where you put the MABRs in the activated sludge tank, the heterotrophs help to consume some of that BOD in the bulk liquid through denitrification, and it allows us to really maximize the amount of nitrification that happens inside the biofilm. And so when we start looking at, well, where does MABR fit as a technology? What are the benefits of it? Understanding this relationship of nitrification rates and bulk liquid concentrations and how that impacts the performance is really one of our key questions, right? And that's what we, as like Black Veatch, my firm, like what we look at is, well, how do we actually fit this into all these different facilities, and what are really the driving design parameters that help us to put this in the right place. So I think this helps to explain maybe some of the dynamics of what's going on inside of the biofilm. And why we're trying to capture this in a hybrid type system. So the value proposition that we see for an MABR technology, part of it is the reduced capital cost, right? So if we can do total nitrogen removal in a single tank, we don't need to have multiple zones. We can do different mixing strategies, potentially need fewer selector zones to do even phosphorus removal, and the ability to retrofit into existing aeration tanks. It's sort of this process, the idea of process intensification, where we could put a lot more biomass on the MABR and have a higher rate system. So that's part of the CapEx component. The OpEx component, you get that really efficient oxygen transfer rates. One of the big things, this is a CapEx as well, is that if you're doing total nitrogen removal in a single tank, it can limit the need for an internal mixed liquor recycle. Right? So a lot of nitrogen removal facilities will have another pumping at 2 to 4 times the influent flow rate to bring nitrate back to the head of the basin. This eliminates the need for that, or at least reduces the amount of pumping that is required. And of course, if we can do the simultaneous nutrient removal, it helps with the supplemental, it helps reduce the supplemental organic material that has to be added into the MABR system. So I'll spend a few minutes kind of talking about the demonstration testing of the -V facility, and it's really looking at addressing some of the key questions to retrofit of the MABR. So if we've got an existing activated sludge tank, or we're looking at a larger type facility, how does MABR fit into that activated sludge process? So Black Veatch is involved in this process really from an applied research angle, where we're helping to validate some of the testing that Fluence is doing, and also providing direction on, well, experimental plan, testing that should be done to help address some of the key questions that we see for application of the MABR in these retrofit type applications. So it's really interesting to see Fluence's demonstration facilities at this MABR Wastewater facility. It's a full-scale wastewater treatment plant. They've done a lot of demonstration testing around the spiral units for over a decade, and the Subre installation is kind of the culmination of that. And so,
Leon, just to interfere, you don't need to finish in 5 minutes. You can go a little longer. That's okay. We don't have a limit on that. So you can feel free to take another 5 or 10 minutes.
Okay. Well, I'll try to still be efficient just to respect everyone's calendar appointment. But yeah, thank you for that, Ronen. So when we looked at the MABR and the Subre application, like the hybrid application, we looked at it from what are the kind of critical knowledge gaps for the MABR retrofit into the activated sludge process. So there's some fundamental questions that we'd be interested in from a research standpoint. I'll get my pointer up here. Oops. So the fundamental questions around kind of community structure, ammonium oxidizing bacteria, nitrate oxidizing bacteria, competition, quorum sensing. There's some really interesting aspects of these kind of counter diffusional biofilms, where you've got oxygen coming from the base and so the other substrate coming from the liquid, that provides some really interesting research questions. And that is still a gap. There's a lot of activity going on that, but a lot of the focus for the Mayans V facility was around like operational challenges. So like, what's the impact of variable influent C to N ratios? How resilient is it to large swings in influent flow rate? How robust is the process to changes in COD concentration? Biofilm management, like as I said, it's very critical to have the right biofilm thickness to kind of limit that heterotrophic competition for the oxygen with the nitrifier. So how do we effectively manage that biofilm? And then the scale up challenges. So if we've got a lot of really good small scale, pilot scale testing, how do we scale that up into, a larger facility, treating the wastewater from maybe 50,000 population equivalent or 100,000 or even down to 5,000. There's just a lot of different scale up issues. Looking at like the number of membranes, how you physically lay them out and the type of nitrification rate. So we've worked with Fluence to try to develop testing plans and analysis to really address a lot of these questions around operational challenges and the scale up challenges. So as Ronen said, Subre is really this sort of retrofit application of the MABR in an activated sludge facility. This is the Mayans V facility outside of Tel Aviv in Israel. And so there's actually two parallel aeration basins. And so this is one of the aeration basins, and this is the second. In November, when I took this picture, there was one of the aeration basins retrofitted with MABR. So it was really interesting because you had parallel facilities, right? So you could really get a sense of energy, performance, and some of the operational complexities of running the MABR. When we look at the overall aeration basin, this is a kind of a two-pass aeration basin. There was an anaerobic selector zone, so that anaerobic condition to try to absorb some of that initial soluble BOD. The MABR towers were placed inside of the anoxic zone, and then you had aerobic conditions around the back end, and you kind of see how that stack that Ronen talked about before is placed into the facility. And so when we worked with Fluence, the idea was, well, what are some of the key questions that we have to actually apply the MABR technology into an activated sludge system like this? So question one that we looked at was, well, what nitrification rate can be achieved in the hybrid MABR? I mean, this is the, from a design engineer standpoint, the really critical part of it, because like I said, the higher the nitrification rate, the less membrane surface area you need, the less membrane surface area you need, the lower the capital costs. There's been a lot of testing around, average day conditions, kind of looking at online instrumentation to look at the hourly flow rate versus the effluent ammonium concentration from the Subre reactor, trying to get a sense of how like a higher loading impacts higher effluent from the Subre reactor. Again, this is not the final effluent, this is just out of that anoxic zone, and trying to balance like, well, how much ammonium do we really remove in Subre and the MABR versus in the suspended growth. Because one of the challenges with pure MABR application is that as you drive the ammonium concentration lower and lower and lower, the nitrification rate goes down as well, because it's harder to diffuse that ammonium into the basin. So what we've been seeing at the Mayans V facility, and this is pretty similar with the other MABR technology providers as well, is that if you target 30 to 50% of your ammonium removal in the MABR zone in your hybrid application, that's really kind of the best spot for a capital cost benefit. Again, that's in a hybrid application where you're retrofitting the MABR into an activated sludge tank. So what we've seen at the Mayans V facility, again, full scale activated sludge, nitrification rate from 2 to 3 grams of nitrogen per meter squared day. That's a pretty consistent number with literature and other manufacturers as well. And it just goes to show that, hey, this really does, the MABR technology provides a good rate of nitrification. It does this in this anoxic zone. The interesting thing is that we talk about the ammonium removal, so this is removing 30 to 50% of the influent ammonium. The nitrate is always below detection. And so we're getting full denitrification all the time, and it's really just the nitrification rate that varies over the course of the day. And there's a lot of work being done right now to really understand the diurnal variability of this nitrification rate and to try to stabilize that. So this one question has been answered with a lot of really good full-scale data to get a sense of what nitrification rate can we really bank on from a design perspective. Question 2 is just what's the oxygen transfer rate of the membranes? And so it's great if we can get this nitrification rate, but how much oxygen are we actually having to add into the membranes, which then helps us to understand the airflow rate. So again, a lot of online testing, this full-scale facility looking at a lot of the different MABR modules and also different depths in the tower. And what we see is that we're transferring somewhere between 10 to 14 grams of oxygen per meter squared day. This correlates to that nitrification rate, and this is just with compressed air, right? So there's very small blowers just right on the kind of deck right here that are operating and kind of pushing that airflow rate into the membranes to get this relatively high oxygen transfer rate into the MABR itself. And so we're starting to develop really good design numbers around this oxygen transfer rate for the MABRs, which helps to establish our airflow rates. Question 3, how should the MABR be mixed? Right, so this is a big question as well. If we're mixing the MABR, do you put mechanical mixers in? Do you deal with it with coarse bubble mixers? How does that integrate into the overall system? And so hopefully I can get this little video to play. So this is actually how it's mixing. So right now, there's a pretty intense mixing cycle in the MABR. The interesting aspect at MAIONS-V is that when that MABR is mixing, there's no airflow going into the rest of the aeration basin. So the idea is that we provide this mixing intensity for a short period of time into the MABR zone. During that time, it's actually just transferring the airflow rate from the rest of the aeration basin into the MABR. And so from an energy perspective, that mixing energy really isn't more energy because you're just taking the airflow from the rest of the aeration basin and transferring into mixing. What this mixing does is 2 things. One is it helps to manage your biofilm thickness, right? So it scours the biofilm to bring off some of the excess attachment biomass. The second aspect of it is it actually transfers the food into that spiral. You can imagine that if you just stuck a spiral in the tank and there was no mixing, there wouldn't be a lot of substrate penetration into the biofilm itself. But with this intense mixing energy, it actually pushes that ammonium into the subrate unit tower, and then that is oxidized. So from a schedule standpoint, this is mixing for about 2 minutes every 15 minutes. And so it's not a large amount of mixing energy, and it's really just a control issue. Like, how do you control that airflow to actually mix the system? And this is similar. There's other ways to mix MABRs. I mean, each manufacturer has their own sort of unique take on it. I think with the Fluence whole package approach of where it's really tied to the overall aeration system is a pretty unique aspect that is maybe more applicable to sort of small to medium-sized facilities, but is a nice way to maybe not need an extra blower to handle your mixing. The fourth question that we're pretty interested in is what are the headworks requirements? I saw some of those questions coming through before. You know, the current applications are really focusing on what I call ultra-fine screening. Maybe it's not ultra, but this 1 to 2 millimeter screens, right? And you're not seeing clogging or accumulation issues with this type of screening on the influence, but this is a big question. And it's other research projects are looking at this with MABR technology to say, well, what if we had a 3 millimeter screen? Or what about a 6 millimeter screen? Do we get a lot of hair? Do we get a lot of material accumulating in the MABR over time? If you get that clogging, it's just going to reduce your effective surface area. So there's a lot of really good work that's showing that, yeah, if you have really good influence screening, you don't have these detrimental clogging impacts on the MABR. But the next step of research is to say, well, what if you don't have as good of screening? How does this impact the MABR? So what have we learned? I think there's been a lot of really good learning around the kind of design parameters that you can look at, how C to N ratio impacts the nitrification rate, how you mix the MABR to manage the biofilm thickness, maybe how you integrate an MABR into an overall activated sludge control system. There are always going to be research questions around site-specific applications and whole system integration. I think there's a lot of piloting that's being conducted kind of globally to answer some of these site-specific questions, but the technology has gotten to the point where we can at least say, yeah, we should be in this range for design. Here's the kind of capital numbers and do our cost-benefit analysis on the technology. So I've already used my extra 5 minutes, but there was one other slide that I wanted to focus on. Ronen spent a lot of time on a spiral, and so I'm going to kind of page through these ones, but there's been a couple of questions on footprint. And so I thought this would be one slide I wanted to spend a minute on and just say, well, there is a benefit on footprint of the MABR. So this is a facility, planning stages where it would look like, well, if we had like a conventional BNR, so we use this S2 EPR configuration, it's just a BNR configuration. So just strictly activated sludge. It's kind of the blue box. The green box is the MABR footprint. And so why do we get a smaller footprint? One, we kind of combine the functionality of aerobic and anoxic zones into one. And so that helps to reduce the overall footprint of the facility. The second aspect is we can actually operate at a slightly lower bulk liquid SRT and just kind of reduce our safety factor a bit. But instead of carrying a safety factor in our bulk liquid, we're shifting that and saying, well, we've got all this extra biomass in our biofilm, and that's where our safety factor occurs. So there is a pretty significant footprint savings that you can have with an MABR, especially if you're building like brand new tanks where you can optimize that layout. So what are we learning about the MABR? What is some of this demonstration testing helping to show us? We've kind of development of a flexible technology to meet multiple drivers, right? So our key benefits are energy savings. We get compact BNR. We get really efficient total nitrogen removal. And then if you have a phosphorus limit, this plays into that overall process configuration and complexity as well. But there are key considerations as biofilm management. I think that was one of the most interesting parts of the Mayan C facility is just developing kind of a control strategy to have really good mixing, but to have it not be a large increase in energy footprint, right? To be able to do that and utilize some existing infrastructure. Hybrid applications seem like a really good fit for a lot of MABR technologies. And again, that aeration control, kind of tying the MABR into your whole system control strategy and making sure you're not just designing an MABR, you're designing an MABR activated sludge system. So that's kind of a high level overview. I appreciate the opportunity to share what we've been learning with Fluence. And with that, I guess, Ronen, do we take a few questions? Or I know there's been a lot of messaging on questions, so I'm sure if we have some verbal questions or if we kind of wrap it up at this point.
So, hey, Leon, thank you again so much for, agreeing to participate in this webinar and speaking about your experience with Fluence's MABR and the Mayan C application. We all appreciate this, of course. As you said, we've seen quite a few questions, and we've tried to answer them all. I now just tried to answer a few of them. Our product manager and marketing manager also has been answering these questions. If you felt like, just due to shortage of time, if you felt like your answer was not answered in the detail that you want, or if I saw many people asking for the presentations and the Stanford report and some other certifications and reports, I'm more than happy. Again, you have my email. Hopefully you should have. Leon, if you will allow me, if you could stop sharing, and then I'll reshare my email. So yeah, thank you, Leon. So I'll share again my email address with you right now. So anybody who felt they still have a question here, you should see my email address right here in front of you. Please, I encourage you to send an email, ask any question you may have, and we'll be more than happy to discuss and hopefully be able to answer your question. Again, as Leon said, we appreciate all of you staying even longer than we expected, the extra 10 minutes. I think, again, we'll answer the questions privately because there are quite a few of them. I don't want anybody to be offended. We did not select our questions, so we'll just answer them one by one. Thank you, everybody, for attending our webinar. We really appreciate it. We look forward to hearing from you, and have a wonderful rest of the day, and obviously stay safe out there with all that's going on. Thank you so much.